So we ended our last video with talking briefly about conservative forces and conservation of energy a little bit. But we can also have non-conservative forces that factor into our problems. One example of this would be friction. Okay, friction is a non-conservative force. If I take my box and I do work to push it this direction, and let's say I just push it to this point, we've used some of the work that I initially put into this box to overcome friction between the box and the floor up to this point. And now if I pushed it past this point, so let's say I push it to a new distance, so that's distance 1, and I push it to distance 2, because I'm constantly fighting friction, I've lost, or I have the potential to lose more energy pushing it all the way to point 2 than to just point 1, right? I've generated, if you will, right? Friction generates heat. I've generated more heat by going to point 2 than I did to point 1. Heat is a form of energy, and that's kind of how we lose energy to friction. Right? So a non-conservative force would be one where the distance, the path we take, does actually matter. Right? So in this case, going just to 1, I lose less energy in my system than I would if I went to point 2. So the path that I took did matter there. Other types of non-conservative forces might even include sound, like a vibrational energy. Okay, if something hits the ground, if falls down, hits the ground, it's going to make a noise, and that noise takes away some of the energy out of that system. And so the more times it hits, the more energy it's going to take off. So again, a non-conservative force there. So if we're going to include non-conservative forces into sort of our conservation equation, if you will, we would have our kinetic energy initial plus potential energy initial, plus the work that we're going to need to do to overcome those non-conservative forces is going to equal our final kinetic energy and our final total potential energy. So we had to add this term here to say that we're going to have to put in work into our system in order to overcome those non-conservative forces and make this system work. The other way to think about it is on the final side of things, we lost some of that initial energy, so this would be like a minus work term over here. And if we take that minus work term and move it over here, then that's plus our non-conservative work. So either way to think about it works. So if we factor in non-conservative forces and everything, we can kind of come up with a whole big general conservation of energy equation that will work for any situation. To do that, I'm actually going to add one more term to our equation. So we're going to have kinetic energy initial, potential energy initial. We had our work done by non-conservative forces, for example, work done by friction. Plus, I'm also going to add other energy initial. This other energy term could be a lot of different things. It could come from a chemical potential, some sort of thermal energy, energy within molecules, whatever. Could come from any sources, just kind of a catch-all for anything that's not potential or kinetic or fits our non-conservative definition. So kinetic energy final plus potential energy final plus all other energies final. And this would be our sort of big conservation of energy equation. So any type of energy problem you can use this equation for. And to make life easy, what you're going to look for is within the problem clues that will let you make some of these zero, right? For example, if we say start in the ground, okay, then I know, well, potential energy is going to be 0 then, right? Because I have no height. Or if we say it's frictionless, then that might mean, okay, no non-conservative forces here. And usually, unless very specifically it's mentioned in the problem, these other energies will be 0 as well. So you kind of start for that. You look for what's 0, and then you're going to plug in the details for your initial and final conditions, solve for whatever the problem's asking for. And by doing that, you can solve a lot of different problems. And occasionally it will actually be a lot easier to approach it this way than it was to, say, use kinematics or just forces or something like that. Power is an important thing for us to look at. Power is the rate at which energy is used. So rate of energy use. So if it's a rate, that means it's per time. If it's a rate of energy use, or actually use the term work per time. Work, remember, was our way of giving or taking energy from a system. So if we're using energy, we're taking it out of the system, or we could be putting it in as well, I suppose. But it makes sense to think of it as taking it out of the system, usually a thermal kind of way. And so work over time. So power, unit-wise, is joules per second, which is equivalent to a watt, which we abbreviate with a W. Be very careful here. If you see something that has a unit of W, that does not mean it goes in for work. Okay, it's a little confusing just because of units, and then one's a unit, one's a variable. So just make sure you're keeping track of that, right? Work is in joules. Energy is in joules. Energy per second, right? So for example, if you have like a 30-watt light bulb, then that means you are using 30 joules of energy to make that light bulb run per second, right? Another unit for joules is horsepower, and unit for power, I'm sorry, is horsepower. And 1 horsepower is equal to 760 watts, to give you a comparison. So you can think about, maybe the horsepower in your car, horsepower of an engine that's needed to do some sort of mechanical work, maybe to lift something up, like engine for an elevator would have to do work against gravity to lift something up. So power, rate at which energy is used, joules per second.